Okay, in this video, I demonstrate the central limit theorem in Excel. Remember what the central limit theorem is. It says that no matter what the underlying probability distribution is, if you take a sample and you calculate the average of the sample, the distribution of these averages will look normal. And it's approximately normal because it becomes more normal as the sample size gets bigger. So let's demonstrate this in Excel. What I'm going to do is roll dice, and it's pretty easy to roll dice in Excel, and I'm doing this randomly using a rand between function. So what it does is give you a number equally likely between the lower number and the upper number. So there you go, I'm rolling dice, and if I go build a pivot table, let me just grab this data and build a pivot table. And I drop the rolling dice there, and I drop it here. And instead of summing, let's count. Build a picture of it like that, and look at there. So it's and I'll refresh this, and you can see. Let's change the scale of this so it doesn't bounce around. Let's put the minimum at 0 and the max at 200. There we go. So anytime I re-roll the dice, you can see I'm getting a distribution that's pretty well flat, because that's what you would expect to get. You should, if you rolled 1,000 dice, about 1/6 of them you would get ones, about 1/6 you would get twos, and then again, it's not going to be exact, but when I re-roll this 1,000 dice, I'm pretty well getting something. Clearly that is not normal. That's not a normal distribution. It's really called a uniform. It's equally likely for every outcome. Okay? All right, now let's change this though. Let's go, instead of looking at this output, let's start taking averages. So I'm going to take the average of 5. And I need to do it enough times so I can draw a picture. So that is taking the average of those. This is taking the average of the next 5. So all I'm doing is now I'm getting a bunch of averages where I'm taking a sample of size 5, sample of size 10, sample of size 30. Now if I look at the distribution of these numbers, what is it going to look like? Well, what the central limit theorem says, it starts looking normal. A normal distribution has a hump in the middle, it's symmetrical, and has tails on the side. Well, let's see if we get that. So let's draw a picture of this, and I've already done it. I've got it hidden, so let me unhide these. So this is my bins, this is the frequencies, and you can see that when you take a sample of size 5, I'm getting these range of numbers. Remember, these are averages now, not actual rows, but averages of rows, 5 at a time. I'm getting some numbers in the middle, and between about 1.6 and 5.6. When I take a sample of size 10 and take the average, my range gets tighter, still centered around 3.5. And then when I take a sample of size 30, the range even gets tighter. So look at the range, this, and then the range of this, and then the range of this. The range gets tighter, it gets smaller as the sample size gets bigger. What that means is that the standard deviation gets smaller. 0.78, 0.54, 0.31, it gets smaller. The average doesn't change, it's always the same, but the standard deviation gets smaller and the distribution. And so if I look at a picture of this, it looks like this. When the sample is size 5, I get something that starts to look normal, but it's wider. And then when I take a sample of size 10, it looks normal, but it's got a tighter or smaller standard deviation. And 30, when it's 30. So the distribution is going to look more and more normal as the sample size gets bigger, but we can lean on the fact even in as small as a sample of size 5, it looks pretty normal, and I can always refresh this. Oh, try to refresh it. There, I'm just re-rolling the dice, it's always going to look like that. There's something that looks fairly normal for the purple, the greens sorta, and the 5 is also. Okay, that's a demonstration of how when you take averages, the distribution of averages looks normal and it has less variability the larger sample size you've got. Thanks.